It's 3:30, and our first speaker today is Peng Cheng.
Okay, thank you. So I'd like to share my screen, share my presentation. Oh, sorry, not this one actually. It's for a different presentation. My name is Peng Cheng. My topic today, just bear with me. I'm trying to share my screen here, if I can. Maybe I'll just do this. Sorry, just bear with me for a second. Yeah, so this is the correct presentation. The topic today is you only look once, real-time volatility regime detection. So here's how this presentation will be organized. First of all, we'll talk about the applications of volatility regimes, and then we'll look at a common kind of regime classification technique, which is hidden markup model. How it works. Of course, it's a classical technique. So, I'm not here to talk about the hidden markup model algorithm, right? But, what are the shortcomings with it, how we will try to address it, and show that the application, when applied to the volatility regime, improves the performance of this model. So, when we talk about volatility regime, I think specifically in the financial market, it's very common to say, okay, we're in a high volatility regime and a low volatility regime, right? Especially in 2020, I think it's fair to say that we've been in a high volatility regime. And, are we now back into the low vol regime? It's not so obvious, right? But it's common for people to say that. But what we find is that generally speaking, if we look at the VIX, for example, it's actually better to classify VIX time series into 3 regimes: high, medium, and low. It may be a little bit obvious later on why that's the case. Okay, but let's say, how do we classify VIX regime, right? Like a common technique would be to use a hidden Markov model. And then on this slide, you'll see that we can decompose the distribution of the log of the VIX into, let's say, a mixture of 3 normals using HMM. And sometimes it's pretty obvious when it will be a high vol regime, when it will be a low vol regime. But in other times, let's say if we're in the medium vol regime, it kind of overlaps with the other regimes, but which is fine. Generally speaking, what we find is if VIX is below 15, then we classify it into a low vol regime, and VIX is above 21, it gets classified into a high vol regime. But anywhere in the middle, it's kind of a medium vol regime. The question is, okay, then why don't we just use kind of these hard boundaries, right, for classification? Why don't we just use 15 or 21? Why do we have to apply some kind of a statistical or stochastic model? The reason is, if you fall in the boundary, let's say a 15 or 21, for example, somewhere near the boundary, HMM actually outperforms, let's say, a hard threshold by a lot, because it's kind of a smoothing kind of technique. So whereas if you use a hard boundary, then let's say if VIX is kind of trading between 14, 15, 16, you may have to, so your regime classification will be very, very volatile. And that's undesirable for many reasons. But a very economic reason is if you were to kind of come up with a trading strategy based on regimes, then you don't want a very volatile boundary, right? You want a smooth boundary. And that is what HMM helps you do. So, we value this feature of the HMM. Okay, that's why we use it, and we find it superior to, let's say, some of the other simpler techniques. So what's the application of, let's say, volatility regime in investing, right? So one, actually a very interesting example is on the application of short VIX strategy. So we probably all know this, just naively shorting 1 month VIX future strategy. There are ETFs on it. XIV was the famous one, and it got completely wiped out, right, in 2018. There are other strategies that are still out there, even for retail investors to implement. And of course, for institutional investors, it's even easier. And of course, before 2018, it was a very popular strategy. But after 2018, it became a little bit less popular for obvious reasons. But let's say if we just implement this kind of strategy, right, but conditional on which regime we're in, based on the HMM classification, then in the low volatility regime, we achieve a Sharpe ratio of over 1. In the high volatility regime, we achieve a Sharpe ratio of -1. In the medium vol regime, it's kind of 0. Okay, so in other words, short vol strategies performs the best in the low vol regime and performs the worst in the high vol regime. So I don't know if it's obvious or intuitive for the audience. Some people that I spoke with found it relatively not very intuitive. But that's just the fact. It's a very strong result. Like in low vol regime, it's favorable to big sudden volatility. High vol regime, not favorable. So as you can see, if we're able to tell which vol regime it is, it has huge implication on volatility strategy. But the application does not only stop with volatility strategies. In a lot of the other studies, volatility plays a very important role. So just to look at some of the other people's studies, let's say in this paper in 2018 published in the JFE, obviously retail trades are all the rage these days, but this was probably 2016, and it shows kind of in terms of the retail imbalance, right, on a stock, if there are more buyers than sellers, then what is the market impact of this imbalance? And in high VIX days, the imbalance impact is much larger, up to 20 days after the observation. And in low VIX days, the market impact is much smaller. And how do they define whether VIX is high or low? They used their median of the sample period as the threshold. So the disadvantage, as I discussed, number one is a hard threshold tends to lead to very volatile regime classification. Number two, if you use, let's say, the median, for example, it's forward-looking, right? Because you're looking at the entire sample. So it's not possible to implement a tradable strategy. Now, they don't intend to do it anyway, but if one were to implement a trading strategy based on, let's say, retail imbalance, then you would need a model for VIX regimes. And this is by no means unique. Not only do we see kind of market impact by retail imbalance have different market impacts in different vol regimes, but let's say we've done studies ourselves on the kind of New York Stock Exchange and NASDAQ market on close imbalance. And we find that generally speaking, strategies based on kind of flow and positioning have very different implications depending on whether the volatility environment is high or low. Okay, so I would say if we can detect the vol regime accurately, then it's very helpful for a range of strategies. So here's the thing, right, with the hidden Markov model. When I speak with a lot of people and let's say, talk to them about the previous slides, generally speaking, I find that hidden Markov model actually don't have a very good reputation among practitioners. And there's a couple of drawbacks. One drawback is hidden Markov model, the historical states are not persistent. So in other words, if I look at the historical data, I fit the HMM once, I get a series of state classification. And then a month later, I use the same historical data plus 1 month, fit HMM again. The historical state classification will actually be different or can be very different. So that is not desirable. But that is kind of relatively, it's solvable, right? You just have to implement an online learning method instead of batch re-estimation. So, in our paper, we address that. We said, here's kind of how you can do it. Again, that's not new, right? But a bigger problem with HMM is what we find is that the model out-of-sample performance is actually relatively poor. So in slide 7, on the leftmost part, you'll see that this is the kind of Sharpe ratios of the VIX strategy I showed you before. And that was estimated in sample. The difference between low vol regime and high vol regime Sharpe ratios are very pronounced, right? But if we do batch re-estimate, in other words, we at every point in time, we use only the data that is before that point, that is before T, and we re-estimate the HMM. and then we look at how the VIX performance is, then it becomes much, much worse. And if we use kind of an online estimate, as I mentioned before, it gets even worse. Okay, so of course, all of the strategies will perform worse out of sample than in sample, but HMM just seems to perform particularly poorly out of sample. And it's not specific to this example, but through conversations with a lot of practitioners, it seems to be the common complaint. So that's the topic actually of our paper, which is to investigate, okay, why is it that it will have such a drastic underperformance when you take it out of sample? And I would say that maybe we found the answer, which is in the algorithm. Of course, the algorithm, again, is very well established, but it crucially depends on forward-looking information, right? So let's say if, imagine a scenario at time t, I observe VIX to be at this value, let's say around 17, 16, for example, right? And then at t-1, it was a lower value. Now, recall that I mentioned that the VIX regime threshold between low and medium is around 15, okay? So if we have only kind of an in-sample data, okay, so we have only data up to time t, then the HMM will carry out a forward algorithm, okay? So it will say, what it's gonna say is, okay, VIX at time t, the value is at the cusp between low and medium regimes. So maybe I'll assign it a probability of 50%, right, to each regime. But at t-1, the regime was low. So it is more likely for the new value to stay in the same regime as the previous value than it is to transition to the next regime, okay? And as a result, the HMM forward algorithm will classify VIX at time t as the lowball regime, as in the lowball regime. On the other hand, if we know the value at time t+1, and it went to, let's say, 19, for example, which would place it firmly in the medium ball regime, then what HMM will do is that it will carry out a forward-backward algorithm. So it will not only look where it was before, right, but it will also look where it is tomorrow. So that if, let's say yesterday it was in the low ball regime, today it's at the cusp, but tomorrow it's very firmly in the high ball regime, then it places a much greater probability for today's value to be for it to have a regime transition, basically, a regime change. So, that's what gives kind of HMM such a good in-sample performance, but such a poor out-of-sample performance. And if we were to do it, we were to estimate HMM out-of-sample, then it is kind of impossible to do this kind of forward-backward look algorithm, right? Because then we will have a forward-looking bias. So what's the solution here? I would say, generally speaking, of course, we don't know what the value is tomorrow, so we will not be able to carry out this forward-backward-looking algorithm. But volatility is actually a very special time series, right? Because it has a very strong memory, number one. Number two, it is relatively easy, actually, to forecast step-ahead value, right? Not only do you have things like Garch, Arch, et cetera, but we now have even more sophisticated techniques and models. So the question is, okay, what happens if we replace the realized value of t+1 at t+1 with our forecasted value? By substituting our forecast value, we create kind of a pseudo forward-backward algorithm for classifying our value at time t. So does that improve our performance, right? So what should we use for forecasting VIX a step ahead? So as I mentioned, Garch is kind of this obviously standard for forecasting a day ahead value if we only have close-to-close data. But we can actually use intraday data and utilize this model called heterogeneous autoregressive model, or the HAR model. So what we found is that, and this is generally the consensus now, with intraday data, the forecast for volatility is much higher than close-to-close. So we choose this model in which it models the day ahead variance as a function of last 1 day, last 1 week, and last 1 month historical realized variance. They're all measured using, let's say, 5-minute returns, right? Intraday returns. And on top of that, for equities, we also add the leverage effect to account for, let's say, on days of low equity returns, we have high volatility, and on days with high returns, we have low volatility. So it's basically a regression of day ahead variance against historical variance of various look-back periods and historical returns of look-back periods. Now, of course, over here, we're interested in forecasting the VIX, not the realized variance. So we substitute the VIX with the realized variance. And statistically, it actually does really, really well. So let's say if we were to do a horse race, right? Let's say using forecasting VIX at t+1, using previous VIX value and the HAR forecast. Now, of course, we know that VIX being highly persistent, previous day's VIX value is going to have a very strong forecasting power, and it is highly significant with a beta of 0.95. But the HAR forecast has a coefficient that is non-zero, number one. Number two, it's positive. Number three, it is also statistically significant. So in other words, it adds value to previous day's VIX in forecasting future VIX. And the R-squared is something like 0.97 in this regression. Okay, so what we would do is we would put HAR forecast into our kind of VIX time series when we run this HMM model. And here's basically the performance of, let's say, a batch estimate of HMM versus if we augment this batch estimation with our HAR model. So this is the confusion matrix of, let's say, if this is our benchmark, right, of how many time periods or how many days are classified into the low, medium, and high vol regime each, versus if we just do batch estimates, how much they overlap. And you can see that, generally speaking, in the low vol regime and the high vol regime, batch estimate does okay, but in the medium vol regime, it kind of struggles, right? Again, really that's kind of tricky. So one shouldn't be surprised that it struggles in the medium vol regime. So there's quite a bit of error. When we augment this with the HAR model, what we'll find is, generally speaking, in a high and low vol regime, performance is similar, but in the medium vol regime, performance is somewhat better. Okay, how much better? It's about, if you look at precision and recall, which are basically the percentage of correct answers by row or by column, then we can probably improve the performance by about 1% to 2% just by adding 1 day ahead HAR forecast. So is it significant? Like 1% doesn't sound like a lot, right? But if we apply it to kind of investable strategies, actually what we find is that it does make a difference. So the upper chart is what you've seen using batch re-estimates without any kind of forecast or forward-looking information. The bottom row are basically the same VIX future strategy, but using regime classification estimated by HAR. And what we can see is that, generally speaking, let's say HAR online model. So this one is the one incorporates HAR, and it performs much better than a simple naive, let's say, online estimate. So that's kind of the result of what we've shown in the paper. Now,
so you have 1 minute left.
Yeah, okay, and just one quick point, which is, we don't necessarily have to be constrained by HAR, right? Like any forecast of volatility can be used. So we can substitute with more sophisticated techniques, and the quality of the enhanced HAR model will be conditional on the quality of the volatility forecast, which is actually a subject that is, very thoroughly studied. And I would say it's not so tricky to kind of improve on this result. So that's basically the presentation that I wanted to give.
Thank you so much, Peng. So I guess I am next. So let me just get to it. And I should mention, people should chat away or send an email. Not quite clear how to interact in an online conference like this. I wish I was in Miami in February. Sounds like a good time of the year to actually go. So this is joint work with Xia Wen, who is a PhD student at CU Boulder, and Max Rohr, who was a visiting PhD student a few years back, who is now in Bergen in Norway. What is this paper about? This paper is about measuring sentiment, trying to color words, and in particular finance words. This goes back to, at the very least, Tellock 2007, who wrote the JF paper, Giving Content to Investor Sentiment, used this bag of word approach, which at the time was the gold standard in the computer science literature. Lauren and McDonald in 2011 published a paper in the Journal of Finance that said, look, these psychology dictionaries that Tellock and others have used, for example, this Harvard 4, have lots of issues. So the word liability is considered a negative word in many of these dictionaries, but is a big piece of the right-hand side of the balance sheet of a firm. So let's try to be more nuanced in finance and accounting as to what we call positive and negative words. And their bag of words approach has been the standard for the last decade and beyond. I myself have used it in at least 3 or 4 papers, should probably more than that. Now, what is the agenda for today? There is nothing wrong with what Bill and Tim did 10 years ago, but what we're going to try to do is take a pretty standard off-the-shelf, I'm going to even call it old algorithm, and see to what extent it can measure sentiment better than this bag-of-word approach when it comes to finance. We're going to be using 2 different corpora. In a 20-minute presentation, I'm only going to be able to show you the earnings calls results. We also have some results on 10Ks. We're actually currently doing a major revision to the paper, and I'm going to show you a few results that are actually not in the draft that is posted. They will be in the draft in our webpage very, very, very soon. And essentially what we're going to do is take a training sample. In the current draft, we do the standard cross-validation 80-20. In the rewrite, we're doing a more as a pricey version of it, in which we just look at a time series, train, say, up to 2013, and then forecast 2014 and beyond. It really doesn't matter. And the basic idea is we train our machine learning algorithm on a particular subsample, and then we're going to try to compete and see if this machine learning algorithm does better than Laura McDonald. There is a play of words here, machine learning versus Laura McDonald. That's essentially what the paper is trying to get at. I will give you the answer. The machines win. They beat the humans, and it's not even close, actually. The R-score is like double in these regressions, which are tough regressions. Predicting stock returns is not easy. In the revision of the paper, which is the new results that I'm going to try to show you, is what drives these improvements, and essentially is this idea of disambiguation and having a larger corpora. English is a very nuanced language, and looking for single words, which is what this bag-of-word approach calls for, has a ton of limitations, and that's what I'm hoping to convince you of in the next 60 minutes. Just going to make a quick comment here. The measuring sentiment in financial text using this bag-of-word approach does have some limits. It's arbitrary. There is some issues with external validity. So, for example, the word close and the word question are actually considered negative in Laura McDonald, but the market closes every day. And if you're looking at earning calls, there are tons of questions. There is some external validity here. Maybe closing stores is a bad signal when you're talking about 10Ks, which is what Laura McDonald looked at. And questioning something in a 10K statement may be a negative signal, but in other corporate that may not be so appropriate. So what are the details of what we're doing? We're going to feed this multinomial inverse regression model off the shelf, implemented in R by Taddy, very easy to run. All the results I'm going to show you today, I can actually run them in my laptop. So it feels kind of cheating to call this machine learning if you can run it in your own laptop, but I guess at some point it was. And we're going to do this fit of this machine learning algorithm, figure out what are the words positive and negative that the machine likes, and then do an auto sample exercise in which we compare the sentiment scores from this machine learning versus the Laurel and McDonald implementation. Main results, I already mentioned, the machine beats the humans. And both words and bigrams have bytes, and I'm going to try to show you the results for this, but bigrams are so much better. Disambiguating in English words is actually very important. I'll give you a few examples as we move forward. Now, the big takeaway from this paper, I think, is that we're going to generate, and you can go check out our web pages for dictionaries, code, and actually a bunch of open source data. It turns out that we can implement our algorithm using Kaggle. It's a big dump of stock returns data, so we don't have to rely on CRISP, Compustat, Italia, which is what we do in the body of the paper. If you want to go and try it on your own, I nudge you to go to my webpage. It's all there. It's version T-1, but the new one is really not. It's just details. So let's get to business. What is the data? Nothing very fancy. We're going to take a bunch of earning calls transcripts. The current draft has 2005 through 2016. We just extended it to 2019. All the results are literally the same. And we're also going to be doing some external validity exercise with 10Ks. I do want to emphasize one important point here, which is earning calls are much more important than 10Ks. Most firms, 90+% of them, do the earning calls before they actually file the formal 10K statement in Edgar. And thus, by the time they're filing this annual statement, it's still information. All the investors learn everything from the earning calls. And that is the main reason that we're focusing on the earnings call corporates. The signal to noise ratio is just much higher. These earning calls have a lot more information than the actual regulatory filing with the SEC. We're going to do a bunch of cleaning, nothing fancy here. Mostly NLP, computer science recipes. Two things that we do different than Laurel and McDonald. We are going to be tagging every sentence. The current version we're using Spacey for that, and essentially to get rid of name entities. If you're talking about JP Morgan, nothing wrong with JP Morgan, but I don't want to be using those tokens as a sentiment variable. Most importantly, and on this particular point, Laurel and McDonald and myself disagree, we're going to be using stemming to reduce the dimensionality of our term document matrices. So words like decline, decline, declining, they're going to become decline. This is with some loss of generality, but it is very standard in the literature. Tim and Bill actually decline all their words in their dictionaries, which it's certainly unusual in the NLP literature. We're going to start, and the body of the paper has all the analysis is basically being done. You take the whole corpora, and we're going to pick the top 10,000 engrams, engrams being combinations of n different words, and just pick those top 10,000. We're going to do some robustness checks. Probably will not have time to discuss them in this short presentation. 10,000 is plenty for the exercise that we're trying to implement. What is the empirical exercise? It's going to be very simple. We're going to take a subset of our data, 50%, 80%, it really doesn't matter. And we're going to train it. We're going to fit this machine learning algorithm, the multinomial inverse regression model. This is going to give us a bunch of loadings of what the algorithm thinks are positive and negative words or combinations of words. And then we're going to take those dictionaries. We're going to do an extra layer, if you wish, trying to reduce the dimensionality of the problem and just say, okay, these words are positive, these words are negative. This is a new dictionary. Let's compare it to the Laurel and McDonald and see how they do. Auto sample on a completely new set of earning calls, see which of these two sentiment metrics actually can predict stock returns better. So before we do the horse race, let's just see what happens if we do the exercise only using the machine learning dictionaries. And what we're presenting here is the results from using unigrams. This is single tokens, just words, exactly mapping one-to-one to this bag-of-word approach that the literature has been using this far. We're going to do the same thing using bigrams, and the same thing using trigrams. And again, these are just combination of 2 words or 3 words. So what do we see in this table? We see that the machine learning algorithm actually can predict stock returns fairly well. These unigrams has a decent R-squared. This is comparable to Laura McDonald, as it turns out. But here's the big bite. Using these bigrams, the statistical significance is much higher in this particular exercise. Trigrams also perform fairly well, but 10,000 is not going to be quite enough. To get deeper into these turn document matrices, when you're using 3 consecutive words, you really have to go a lot more than 10,000. And our calibrations suggest that the benefits that you have with these diagrams do not really overcome the extra computational cost. Not in this presentation, but I will hope you would trust me in this statement. Okay, so now let's do the Laura McDonald horse race. So this first column is trying to predict out of sample these stock returns reactions to the earning calls using the Laura and McDonald dictionaries. Both of them load the positive and the negative. The negative a little bit stronger, which is very typical for this type of empirical exercises. And the R-square, as I was mentioning, not much higher than what we had before. Now, what happens if we put in the machine learning unigrams? And remember, these were not the strongest. The bigrams were actually the strongest, but let's throw them in and see what happens. Well, it turns out these machine learning dictionaries of just single words do at least as well as Laura and McDonald. Their R-square increases fairly big. The t-stats for both positive and negative are the same magnitude, maybe a little bit bigger, sometimes a little bit smaller. Now with the unigrams, it's very easy to actually consider those that overlap and don't overlap. You could be thinking, okay, the machine is just discovering exactly the words that the psychologists or Laura McDonald picked out 10 years ago. Well, let's just kick out from the machine learning dictionary all those words that do not appear in Laura and McDonald and see how things look. And you can see that the statistical significance of these completely new words do seem to have a ton of bite. Now, what happens if we throw in these bigrams? The bigrams results are basically showing that the machines are measuring sentiment a lot better than Laura and McDonald. I do want to highlight the size of the coefficients here. I've normalized every single right-hand side variable to have unique variance, and a 1 standard deviation shock to the machine learning sentiment moves the stock prices by 1.7% on the positive side versus 24 basis points for Laura McDonald. And on the negative side, the effect is also 3 times bigger. So it's clear the machine has a lot more to say about the color of these earning calls than the current bag-of-word approach. So what I want to leave you with in the next 5 minutes is why is the machines doing better than humans? Lots of different moving parts here. We have slightly bigger dictionaries, although this is not critical. You can start with very small turn document matrices, and the algorithm is still going to do very, very well. But it's picking up something more, and this is what I'm going to try to show you exactly what is it picking up. So here is one of our favorite examples, and there's tons like this, is the word demand. Nobody would actually say that the word demand has a positive or a negative color. It's, demand and supply. We're economists. This is one of our building blocks of the profession. You have demanding customers too. It's a pretty nuanced English word. So you wouldn't want to count it in a positive and negative dictionary. Now let's see what happens if you start looking at bigrams. And I'm going to pick here, I'm presenting the frequency across all our corpora as well as the actual loading in this multinomial inverse model, and they're sorted by the loadings. I think if I told you that you heard the word solid demand in an earning call, that probably means something positive. Whereas if the CEO says soft demand, that probably is a negative word. The machine learning algorithm picks that immediately, even though it doesn't have that many observations, but it's such a salient, negative word to say soft demand, weaker demand, reduced demand. Whereas we can classify all these other healthy demand as clearly a positive word, right? These bigrams are being able to disambiguate and color the token demand in different ways. Demand is a good example because about half of the tokens are positive and half are negative in the fitted model. And you can read through this and scratch your head and say, well, maybe this thing is picking up something that Laura McDonald didn't pick up. Here are some other words that are actually interesting. I'm going to focus on deliver and leverage, which also are words that nobody would actually say, well, that doesn't sound positive or negative to me. Well, it turns out, let's just consider deliver. In the fit that I'm showing you here, which has over 20,000 TDM, the size of the terms, deliver has associated with it over 100 different bigrams. 38% of them are neutral. The rest are virtually all of them positive. If you're saying deliver, it's because you're delivering something. And the same thing with leverage and many of these other words that I'm listing in this table. If you're leveraging something and you use that word in the context of a conference call, that's going to be a positive word. And the same thing goes for negative words. If you're talking about competitive something, it's probably a bad thing. If you're talking about pressure, that's probably a bad thing. As a matter of fact, pressure has 30 bigrams associated within this fit, and virtually all of them are negative. And you don't want to be discussing pressure in an earnings call. I have a list of positive and negative bigrams here that I'm going to skip. And this graph is going to take a little bit too long to explain. It's trying to get at how the unigram fit does not capture the color that bigrams give you. Bigrams can actually disambiguate these tokens a lot better. In here, I'm basically highlighting that even if you start building term document matrices with over 1 million terms, trigrams are really hard to cover the whole corpora. For the main analysis in the text, the bigrams only cover 50% of the full text, but do seem to be able to color things a lot better than unigrams, which is the red lines here. With 2,000 unigrams words, you can cover the whole thing. They just don't have as much color as these bigrams. One small point here, the machine learning algorithm does seem to be doing fairly well with turn document matrices anywhere from 10,000 all the way to 100,000. And these are things that you can actually run in your laptop. It's not computationally that expensive. I did want to at least show you this graph. I've argued with Tim and Bill about using 10Ks versus earning calls. These are abnormal returns on the earning call days, blue dots, versus 10K days. The red points here is pretty obvious. The information is coming out on the earning calls dates, not the 10K releases dates. Let me just finish up. I have 1 minute left with one last example. So Laura and McDonald think and say and argue that optimistic, or any other decline variation of it, is a positive word. Well, it turns out that most of us would probably agree with that, but the machines don't. The machines say that if you are using the bigram remain optimist, that's not that great. You're cautiously optimistic. Maybe you're actually being positive, but remaining optimistic seems to be a negative signal. Similar examples here. To make a best estimate is not a great bigram in these earning calls. To conclude, we've implemented this off-the-shelf machine learning algorithm to see if we can measure sentiment in text better. it does seem the auto sample performance argues overwhelmingly that these algorithms do much better on these backward approaches. And it could be because the stock prices, which is what the machine is using to supervise the labeling of positive and negative terms, are better at reading text. But probably more importantly, this idea that English is a complicated language, and disambiguating these single tokens goes a long way in measuring sentiment in text. And our next speaker is Will Kong. Will, the floor is yours.
Hi, Diego. How are you doing? Thank you. Great paper. I really enjoyed it. Let me just share my screen. I have more questions. I'll email shortly. So could you see my slides here? Yeah. Okay, perfect. I'll start. Oops. Thank you very much for having the paper on the program. This is joint work with Ke Tang, who's at Tsinghua University, and two computer scientists, Jingyuan Wang and Yang Zhang, who are from Beihang University, also in Beijing. And in the earlier sessions, we actually have seen quite a bit of discussion on reinforcement learning. Deep learning neural nets, those are synonymous, but deep reinforcement learning and all that. So here, I hope I can convince you that there is a natural application in finance that's very much economically driven. We're not pulling a cutting edge tool just for the sake of using it, but they are cutting edge for some reason, and we want to show those drivers actually enable us to solve some age-old problem. So what is the age-old classical problem we have? Portfolio management. And I'm going to make a claim that most of the existing approaches take a two-step approach. What do we do? First step, we estimate distribution return. So, risk premium, recovering the pricing kernel and all that. And it's typically done through a supervised learning approach, right? Regressions, you name it. There are different ways of doing it. So for that, I'm just going to call, X, Y, what we observe in the data. C is the parameter. F is the function that we're trying to estimate. Let's say, if you are estimating risk premium, or actually, if I'm minimizing pricing error, Y would be the observed return in historical data. And this F function is just our predicted return. And we're trying to minimize the error, right? And after that, we know from Markowitz Nobel winning piece how to do mean variance optimization. That part is clear. Sometimes we don't use that. We focus on risk alone because mean is expected return is hard to estimate. Then we go to risk parity. Sometimes we do ad hoc weighing, equal weights or market weights, and then we maximize, optimize what we want to do. We're optimizing the portfolio construction in order to achieve some outcome. Here, Z would stand for our portfolio construction strategy. We want to figure out a portfolio construction that maximize some performance metric. Now, what's wrong? Well, it's not quite wrong. What's limiting about this approach is minimizing the pricing error in the first step is not always equivalent to maximizing the reward later. So this is a two-step approach. And empirically, we know the first step involves very big estimation errors, and it's hard to get rid of. So what we want to do here is we want to do a direct construction. Can we construct the portfolio directly without going through the intermediate step? So the natural question is, can we do this through supervised learning, traditional supervised learning? Well, if we try to do it, there is a inevitable step of separation in the sense that I want to maximize my performance metric, and I have to figure out basically my strategy function, even if I were to do it directly. Okay, the objectives are aligned now if I try to estimate this, but empirically, what's the challenge? The optimal strategy, construction strategy, is not something we observe historically. In other words, it's not labeled data. So it's very hard to use supervised learning to do it. Or at least it's not, we don't observe the historical optimal portfolio constructions. We observe some portfolio constructions, but there's no good reason to believe they are the optimal one, right? So in that sense, there's some gap between this supervised learning approach, even if we were to directly estimate or optimize our portfolio. I'll show you the literature. There are some earlier pioneering attempts, but under supervised learning, there's limited what we can do, at least empirically. And supervised learning wouldn't incorporate interactions of the trading action and the environment. And that's where reinforcement learning would come in. If we think about what are the defining features to reinforcement learning, and actually from Sutton Buttle's book, page number 1, there are 2 defining characteristics. One is the trial and error search. The other one is the delayed rewards, which could incorporate interactions with the environment. We don't have to include that part. I mean, all the cool applications in AI, in self-driving car, computer vision and all that, they include that interaction, AlphaGo. But delayed rewards could be without the interaction with the environment. That's fine, depending on what we need when we construct a model of the environment. Now, here, searching for the optimal portfolio construction through trial and error would make great use of reinforcement learning and potentially allows interactions between the action and the environment. We can take into consideration price impact, dynamic budget constraints, even time varying preferences of the investor or portfolio manager. So that's kind of why we want to take a reinforcement learning approach. And this is the literature that's very much related. Our paper is close to a series of papers by Brand and co-authors. They take the supervised learning approach, and if you take the parametric approach, there's still the problem of misspecification. It's not to say that supervised learning wouldn't work. If you specify the model very nicely, and it could work great, but how do we know which one is going to work better empirically? We don't know ex ante. Now, if we take a data-driven, non-parametric approach, traditional supervised learning approach wouldn't allow us to accommodate a high dimensionality of input variables, as the authors themselves point out. So that's where we want to bring in the deep part, right? The neural net version of RL. I mean, if we look at all the recent machine learning applications, if I may make an attempt to group them, it either falls in this dimension reduction approach, or making the model more robust by taking a semi-parametric or distribution-free approach. And we want to bring in neural nets here because financial data are very different from science and engineering data. High dimensionality, nonlinearity, those are common across different disciplines. But in financial environment, or even social science in general, we have much lower signal to noise. We have a lot of interactions, endogenous interactions of variables, rather than the sparsity problem that computer scientists typically have to deal with. We typically have fast non-station dynamics. All these would make a neural net approach make sense, because they would allow us to accommodate many of these issues. And one key innovation we want to make in this paper is actually the fact that we're dealing with panel data, right? All these, as you'll see, we'll use a transformer encoder or long short-term memory. These are sequence models. They are designed in science and engineering fields for single sequence. When we're seeing translation, we're reading through the passage line by line. But when we manage a portfolio, we're dealing with multiple assets. So we're dealing with panel data. And our key innovation here, one of the key innovations here, is to introduce cross-asset attention network that allows us to deal with basically the neural net version of panel data analysis. Okay. We also hope to provide some interpretation of our model, because most of the machine learning or AI models tend to suffer from this critique that they are complex and black boxy, and it's important to develop economic interpretation. And our key idea there is just to project a complex model onto a simpler modeling space. Right? I could have a very complicated neural net model, but I can project that onto, let's say, linear regression model that's more transparent. And related to what Diego was saying, for natural language processing, you can even project complex model onto natural language space to look at what people are talking about when the model takes certain actions, taking long positions or short positions in assets. So that's something we hope to add to the literature as well. So so let me go into the model. I know it's always a limited time here. So here's what we are taking from existing models. We're going to use transformer encoder, as well as actually long short-term memory models. These are single sequence models, the most cutting edge. Why do we want to use them instead of just regular RNN or some earlier models? Because they've been proven to work very effectively in many other applications. And let's say I look at asset I have, let's say 12 months. K stands for the time period that I look at. 12 months of the, say, firm characteristics or market signals related to asset I. Transformer encoder is just going to encode that into some abstract representation. Right? That part we don't innovate. That's just taking the model directly. But with that, we're converting time series for each asset into a representation using neural nets. And after that, that can be put in the general category of sequence representation extraction modules. After that, we build the CAN cross-asset attention network. The idea is the cross-section of asset matters. So we're going to create a very flexible model structure. At the start, there's little economics there, right? It's just a very flexible model structure. We're going to use that to generate what we call winner scores. We're going to take long position of the high score stocks, short position of low scores, and use that to generate portfolio. Now, portfolio, let's say we use auto sample Sharpe ratio as our criteria. The portfolio is going to perform horribly initially, right? Because we are randomly initializing the parameters. But that's where the reinforcement learning comes in. The model is going to generate portfolios. We're going to give a feedback. If it's high Sharpe ratio, we'll give a thumbs up. Otherwise, we'll give a thumbs down. Eventually, it's going to converge to the parameters of the model such that it generates good auto sample Sharpe ratio. Right? That's the whole reinforcement learning procedure. So I wouldn't be able to go into the details here, but the cross-asset attention network structure is very similar to self-attention. We're dealing with a single sequence. We're basically allowing the earlier sentences to take a dot product with the later sentences to see how they are related. Right? Attention can be allocated across this long sequence of information. But here we're just doing it in a cross-section. But the idea is very similar. That's kind of the basic structure we put forth. Empirically, we can test this on many different assets. Here, we're just going to use US assets. Input variables are very standard. Here we pick 51, following this recent paper by Freiberger and co-authors in RFS. 51 and 12 months window. So it's 12 times 51 input variables, very high dimensionality. And the sequence modeling would allow us to capture time, past dependence, right? Time series information. CAN would allow us to capture more cross-asset relationship once all these inputs are passed through the model. When we talk about interpretation using text, using natural language, we use filing such as 10K, 10K. I probably wouldn't have time to go into that today, but that's the data source. So here's the main table, main result. AP stands for alpha portfolio. All means all sample from 1965 the training set is until 1989, and the test set will be 1990 onwards. I don't need a separate model validation set because we're doing reinforcement learning. You can look at different subsamples as well. So here's the performance. Bigger than Q10 means I'm excluding the bottom 10%. Bigger than Q20 means I'm excluding the bottom 20% in terms of market cap. So we don't want the small illiquid stocks to drive the results. And these are all auto sample. If we use OOS Sharpe ratio as the criteria to train the model, and when we test it auto sample, these are the performance, which is quite high, over 2 consistent, even after excluding small stocks. Maximum drawdown turnover is a very small. Average holding period is about 4 months. We're doing monthly rebalancing, so it's not relying on high frequency trading. You might wonder how the capacity of the alpha portfolio strategy is. Here we're not modeling price impact, but in an extension we could do that, right? That's the flexibility that reinforcement learning offers. We can also control for various risk factors. These are annualized alpha that are also consistent above 13%. Where does this superior performance come from? We can do a transformer encoder two-step portfolio construction, right? Yes, transformer encoder helps, but the single step direct construction helps as well, because otherwise we wouldn't get such a high auto sample Sharpe ratio. Similarly, we can compare it with the benchmark model that use similar inputs, and we do have consistent outperformance after excluding small stocks. But to the author's credit, their goal was to minimize pricing error rather than optimizing the portfolio performance per se. This works across different episodes or time periods for different sentiments, VIX, or market illiquidity episodes. So it's not driven by a liquid period in the test set. We can look at the Sharpe ratio across time and the risk-adjusted alpha across time. It could be that certain anomalies are traded away, but still overall the auto sample Sharpe ratio is above 2, mostly above 2 in the sample. It's not driven by long short portfolio. If we do a long only portfolio, the performance is still there. We can exclude unrated and downgraded ones using alternative definitions of transaction cost or turnover measures. And importantly, it's possible to put in transaction costs, price impacts. You can even define different objectives, such as if the fund loses 50%, it's going to go bust. As in the training process, you can even use managers' compensation in the training process. That's the power of delayed reward feature of reinforcement learning. So I have 2 more minutes. I'm just going to mention a few things we did to interpret the model, right? Fine, it seems to perform quite well. What exactly is the model doing? So the first, we call it economic distillation. The first idea is just to, we know for neural nets, we have a feature importance analysis. We know which feature contributed the most in terms of how much it pushes the objective in the steepest ascent, right? If we are doing optimization. We basically pick those important features, take their higher order terms, take their interaction terms, dump everything into a linear regression. You can use lasso and ridge and elastinite to select variables to keep things still reasonably transparent. But we're back in the linear regression model. Basically, this mimicking model does not perform as well as alpha portfolio, but it behaves similarly. And by looking at this model, we can see what are the key features, which higher order terms matter. IVC here is inventory change, scaled by total assets. And it turned out that it's related to a accounting paper published in 2001, but it hasn't been traded away much. We can also see rotations between market signals and firm characteristics. By market signal, I mean price or daily volume inputs, things like that, maximum return, daily return. these are just different features, how important they are throughout the test period.
So Will, you have about 0 minutes left.
Okay, so I'm going to just go to the conclusion. Another projection one could do is through textual analysis, but I'll skip that. So I'm just going to end here. Just want to say it's an alternative framework for portfolio management. It does make use of cutting edge AI tools, but it's important that we tailor it for financial applications. And finally, it provides some procedures for interpreting black box models. Thank you.
Thank you, Lynn. That was a great presentation. So our last presenter today is Lynn Fei from the University of Carolina, Charlotte.
Oh, sorry. So hello, everyone. It's a great pleasure for me to present the paper here. This paper is about the serial dependence of the commodity futures returns based on a machine learning approach. This is joint work with Dr. Yufeng Han. So now let me discuss some background of commodity futures markets. So historically, commodity futures were primarily used by farmers and producers to lock in the price and to reduce the risk financial losses. However, over the past 2 decades, that is after 2004, financial institutions have increased their exposures to commodities dramatically, making them behave more like financial assets. These investments include ETFs, ETNs that yearly track the price of a single commodity, or a broad basket of futures index. And also commodity trading advisors also mainly use trend-based strategies. So this figure shows the asset under management for the managed futures industry. So as shown in this figure, after 2004, the asset under management has increased dramatically. So in this paper, I call this period is referred as a post-financialization period by researchers. So this paper mainly studies 2 questions. 1, whether lagged returns contain predictability. 2, what explains the predictability of the lagged returns. Here's the motivation of the paper. First, many commodities have economic links that can drive the lead-lag relation among futures returns. For instance, heating oil and gasoline are refined from crude oil. So it is possible that the lagged returns of crude oil futures can be tied to the returns of heating oil futures. Next, crops are used to produce biofuels, which are substitutes for fossil fuels. So there can be lead-lag relations between crops futures and energy futures. There are a large amount of literature studying the spillover effects between them. My next motivation is about the increasing speculative trading during the post-financialization period. For instance, Da Tang and Wu 2020 find that during the post-financialization period, there are sentiment spillover among index futures. This causes price reversal for index futures, but this relation doesn't exist for non-index futures. Gong et al. 2020 find that speculators' spreading position can negatively affect commodity returns. Researchers also find excess contemporaneous movement during the post-financialization period. My last but not least motivation is that the majority of CTAs are trend followers who chase time series momentum or other trend signals. According to Llewellyn 2002 and other researchers, momentum is probably caused by the lead-lag relations between the securities. So this paper is a natural extension of the above literature. That is, we examine the lead-lag relations among a broad set of commodity futures and exploit the predictability. So this is the first one to directly analyze the predictability of the lagged futures that allows each individual futures return to respond to the lagged returns for all the futures. Next, we also use machine learning techniques to overcome the potential overfitting problem. So in this paper, our focus of the machine learning techniques is the most simple one, that is lasso. We also find much better performance than the two diversified commodity indices, such as S&P GSCI index and the Bloomberg commodity index. Both of them has a annualized excess return that is negative. So we assume each futures returns are affected by the first and the second legs, where the lagged returns include its own lag as well as other futures lags. So we also, in the robustness check, we also include the third leg. And our results are robust to the number of legs. So in our full sample, since we only focus on the post-financialization period, there are 192 months in the full sample, and the number of predictors, 54. And in our out of sample result, we use 60 months estimation window and to estimate next month, to forecast next month's return. So apparently a large number of predictors can cause overfitting problem. So that's why we use lasso in this our paper to study the lead lag relations. And in the main analysis, we use AICC to select the lambda so that we don't need to shuffle the data because we are doing a time series regression. But we use cross-validation to estimate the lasso anyway, and the results are robust to cross-validation. We also use OLS post-lasso estimation to reduce the bias of lasso coefficients estimates. So in the full sample, there's simply one OLS post-lasso regression using all the sample period. And as for out of sample estimation, it is one step forecast and with fixed window. So we studied 27 commodity futures that are actively traded in the US. All the data are collected from Bloomberg. And when we calculate returns, we don't across contract. This table shows summary statistics. Let me skip summary statistics. So table 2 shows the full sample results. There are some lead lag relations that make sense. For instance, there is first order autocorrelation for crude oil futures. Moreover, gas line return is selected to predict corn, which may probably because the relation between biofuels and fossil fuels. Moreover, lean hog is also selected to predict corn, mainly because lean hogs consume corn. However, there are some unexpected lead lag relations. For instance, the lead lag relation between feeder cattle and gas line. Apparently, there's no economic links between them. So as shown in the full sample, these selected effects are sparse and sometimes unexpected, which is consistent with the financialization story. According to Basak and Pavlova 2016, the correlations between commodity futures prices goes up with financialization. There are also a lot of researchers studying how index futures add noise to commodity futures markets. And this paper, our methodology also follows this paper closely. Chinko et al. 2019 also identified a set of unexpected lagged returns as a predictor for the individual stocks, but they use a 30-minute interval. So as for the out-of-sample analysis, we consider two trading strategies. The first trading strategy is a single source strategy. That is, we buy the five futures with the highest forecast and long and short them with the 5 lowest forecasts. As for the timing strategy, is a moving average strategy. We long the futures with positive forecasts and short them with a negative forecast. We have two different versions of lasso. The first version of lasso includes only the futures with at least one lagged returns as a predictor. Lasso all uses all the commodity futures, including those with intercept only as the selected effects, because sometimes Lasso doesn't select any predictor, but the intercept. The two benchmark portfolios include prevailing mean, which is simply the historical moving average, or OLS, with all the lagged returns. We also have other benchmarks such as momentum basis or predictors or other predictors. But here, just focus on the two benchmarks. So table 3 shows the performance of the single source portfolio. the two Lasso portfolios apparently outperformed two benchmarks with annualized excess return around 15%, and the downside risks are also much smaller than the two benchmarks. And the risk-adjusted returns are very significant, which are around 15%. And the R-squares are very small, which means the existing factors cannot subsume our Lasso performance. Table 5 shows the performance of a timing portfolio. Here, the magnitude becomes somewhat smaller. Part of the reason is that in timing portfolio, the precision is $1. So to make them comparable with the previous sort portfolio, we can multiply those number by 2. So the Lasso portfolio generates an annual excess return around 12%, which is still relatively large. The annualized alpha, if we multiply this number by 2, then it's around 15%. So the results of the timing portfolio are comparable to the single sort portfolio. Next, we try to see whether index trading or financialization indeed causes the predictability. So in table 7, we redo the out-of-sample analysis based on indexed futures only. And we find that the Lasso portfolios still perform very well in the indexed futures. When we use non-indexed futures, we find that the performance of the Lasso portfolios disappear. Table 9 is an in-sample analysis. That is, we interact each lagged returns with a ETF inception dummy, which is equal to 1 after September 2006, otherwise 0. Because after around September 2006, several ETFs that tracks the either Bloomberg index or GSCI index are incepted. Then we test whether the interactions are jointly equal 0. So as shown in this table, we know that at least one lagged return is selected for 14 out of the 16 index returns. And among the 14 futures, 10 out of the 14 futures have interaction of ETF inception dummy with lagged returns as selected effects. And for all of these 10 futures, the F statistics can reject the null hypothesis that they are jointly equal to 0. So based on the results from table 7 to table 9, seems like financialization and also index trading indeed explains our results. So our robustness check, we tried different Lasso models, such as two-stage adaptive Lasso, elastic net, and combination Lasso, developed by Han et al. 2019. We also tried to use cross-validation to select penalty parameters. We also tried to add more lags and adjust for seasonality by adding 11 month dummies. Our results are all robust to all these different linear models. Next, we try to explore tree-based model and neural networks, because this model accounts for non-linearity and interaction between variables. And for neural networks, we only consider one layer because our sample size is so small. Table 11 shows the results of tree-based models. The single sort portfolios perform okay, but the timing portfolio perform horribly. So similarly, in table 12, we find that when we use neural networks, the single sort portfolios with few neurons perform well, but not timing portfolio or single sort with more number of neurons. Well, the results in table 11 and table 12 shows that these more complex model perform worse than Lasso, indicating that non-linearity do not exist in our data. So our finding is also very similar to this paper, Filippo et al. 2020, who also find that in their small exchange rate cross-section, neural networks perform worse than their elastic net in predicting exchange rate. So to conclude, we find that the lagged commodity futures returns contain valuable information and can help forecast the returns of the commodity futures. We also find that Lasso helps identify useful and important predictors. Lasso portfolio can generate significant out-of-sample return. Finally, we find that financialization causes the excess movement among commodity futures returns. So I look forward to your comments. You may also send your comments to my email address. So that's all my presentation. Thank you.